Today we're going to keep talking about the energy principle, not surprisingly. And what we're going to talk about today is two things. We're going to talk about situations where rest energy actually does change. And then we're going to talk about potential energy, which is a pretty important topic. Since this is a second fundamental principle, you shouldn't be surprised to learn that you're expected to know this. So the energy principle written one of these ways, the definitions of particle energy, kinetic energy, rest energy, and work are things that you need to know. And I think that you're just going to be working with them enough that you will know them. But so up to now, when we applied the energy principle in simple situations, we had balls going up or down or things like that, and the rest energy of an object didn't change during the process we were interested in. This isn't always true, though. There's a lot of things going on around us all the time in which rest energy actually does change. So, for example, in the sun, we have fusion reactions where we have hydrogen and deuterium, that's heavy hydrogen, right? It's got a proton and a neutron. It's a train. In the nucleus, combined to make something that's completely different. Helium, a different element. It actually has two protons in the nucleus. It's the main process going on in the sun that produces all the energy, that releases all the energy that we get from the sun. People keep trying to do this on a scale that actually would produce power in a practical way here on Earth, and people have been working on it for a long time, and they're getting better, but no one's really quite got this going yet. On the other hand, fission, where some atomic nucleus splits and forms two other atoms. The most common we know about uranium-235, which when it's tickled by a slow neutron can split into, it can split any number of ways. So it could split into a couple of palladium nuclei. It's one mode there, and there's some neutrons around here too. It could split into something like barium and krypton. So that would be barium's 141, and krypton I think is 92. So the actual nucleus can just fall apart and release energy. Interestingly, and there's more of that going on than you might think. Most of the energy we get here in Raleigh comes from the Sharon-Harris nuclear plant, which isn't very far away. So nuclear reactors are powering these lights, most likely. There's a little research reactor just right down the street in the Burlington Nuclear Labs where people do research on involving the products of nuclear reactions. So this is something that is technologically going around us all the time. An interesting example of a nuclear reaction actually is that despite the fact that neutrons are very stable when they're in a nucleus with lots of other protons and neutrons, an isolated neutron that isn't close to anything else is actually unstable. And it sits around on the average of about 15 minutes, and then it falls apart into a proton and an electron and a very low mass particle called a neutrino. This is an antineutrino. It's an antimatter particle. And in these reactions, in processes like this, we have a change of rest energy. And how can we tell that we should pay attention to changes in rest energy? Well, we have different particles in the final state than we had in the initial state. Okay, we started out with uranium, and now we've got some palladium nuclei. We started out with hydrogen, and all of a sudden we've got helium. We started out with a neutron, and now we've got a proton, an electron, and antineutrino. So they change, the substances actually change their identity. They change from one thing into another. When that happens, then typically then you have to worry about rest energy changes. There's almost always a conversion of some of the energy that was in the rest energy of one of these things into kinetic energy of the products, or the other way around if we're going. So let's actually just talk about one of these in detail just to show how we'd work it out. Basically, there's nothing more to it than we've done before. Once you pay attention to the fact that the rest energy is probably changing, then you just write down the energy principle, include all the terms, and you're basically done. So it's not hard to solve problems of this kind. It's very straightforward, but you just have to notice that you need to do it. So let's consider neutron decay. We have an isolated neutron sitting off in outer space somewhere. It'll do this even if it's not in outer space. And after 15 minutes or so, on average, it decays into a proton, electron, and antineutrino. Okay, you know what protons and electrons are. What are neutrinos? Neutrinos are elementary particles that don't have any electric charge, so they don't interact electrically. They're not made of quarks. They're what are called leptons. They're like electrons in that regard. So they don't interact through the strong force, so they only interact through the weak force. They're actually pretty hard to detect. Since they don't interact very well with things that are charged or things made of quarks, it's just kind of hard to find them. They interact infrequently. So it took people a long time to actually be able to detect them. The reason they were discovered in the first place is that some processes were going on where people applied the energy principle and they said, wait a minute, this isn't working out right. If I add up all the energies, I'm missing something. And instead of saying, well, the energy principle doesn't work, they said, I bet there's another particle we can't see. And then it actually took decades to be able to detect it. There's now a project, there's been recently a project where a beam of neutrinos generated at Fermilab, just outside of Chicago, is actually shot underground all the way to a mine in Minnesota where there's a big, huge, massive detector that tries to detect them. And what people are looking for there is to try to see if they can figure out what the mass of a neutrino is. For a long time, people thought maybe neutrinos were like photons, like light particles, and they didn't actually have any mass. But then people started to think that their theories would hold together a lot better if they actually had some mass, but we've had trouble measuring it so far. All we know is it's very, very tiny, and there might be there's three different kinds, and we're not exactly sure who's got what mass, but it's very small. So basically, not much mass, but they can have quite a lot of kinetic energy. So okay. So let's just apply the energy principle to this equation. So we're going to say E final is E initial plus work. And you might think, well, gee, how do we do this when we've got different stuff on different sides of this equation? What do we choose as the system? And the answer is it's okay to choose all the particles as the system. So the system is whatever you've got here, and if it falls apart into these, well, then these are the system. So the system is everything you started with and everything it turns into. So that turns out not to be a problem. And so what we're going to do is we're going to write the energy principle, E initial, E final is E initial plus work done by the surroundings. And since we can define, since we're going to take our neutron in outer space where it's far from anything, there really isn't going to be any significant work by the surroundings. So in this case, it's 0. Even if the neutron was right here near the Earth, despite the fact that the Earth is exerting a gravitational force on the neutron and on these products, if we just take our initial state right before it falls apart and our final state right after it falls apart, the Earth hasn't had time to do much work. And we're going to consider the initial state where all these things are. What happens when the neutron decays is all these things fly out in different directions. We're going to take the final state where they're very far apart, and by the end of the class we'll see why we had to do that. So we're going to take the final state when they're far apart. And what we want to find out here is what the kinetic energy, the total kinetic energy of all these things is, starting with a neutron at rest. Okay? Now we need to know some things. We need some information. But before we start plugging in numbers, so we have, we'll write down the numbers we know just so we've got it recorded here. So the rest energy of a neutron is 939.6 million electron volts. What the heck is an electron volt? Well, a neutron is small, so if you work out mc squared for something that has a mass of 10 to the minus 27 kilograms, it's a small number. So we often use a different unit of energy called an electron volt, EV, electron, and it's equal to 1.6 times 10 to the negative 19 joules. And a million, an MeV, a million electron volts, is just 10 to the 6th electron volts. And so people often talk about the rest energies of things like a single neutron or a single proton in terms of million electron volts rather than in terms of joules, just because it's a nicer number. It's actually just easier to work with. So let me make sure I've actually got this right. Yeah, that's right. And so the rest energy of a proton isn't a whole lot less, but it's a little bit less. It's 938.3 million electron volts. And the rest energy of an electron is very much less, 0.511 million electron volts. And the antineutrino, we're not really sure. It's probably something on the order of 1 electron volt, so that makes it something like 1 times 10 to the negative 6 million electron volts. We're not enough to make a big difference here, but its kinetic energy can be significant. So we have that data, and so now we're going to have to figure out what the kinetic energy is. So what we're going to work on is just writing out the energy principle. When we solve a problem involving energy, we write down the energy principle, we define our system, and the next thing we do is we just fill in all the terms that go in each of these things. So here's our first question. We have this neutron decaying. The initial state we're going to take is the neutron at rest. The final state is all this stuff far away. The system is all the particles. And the question is, what quantities do we need to put into this E initial energy here? And so the choices are, these are the kinetic energies of various things: kinetic energy of the neutron, kinetic energy of the proton, kinetic energy of the electron, kinetic energy of the antineutrino. And these are the rest energies of the same thing. So the question is, what goes into this E initial? You need to know fundamental principles. We give you all the we give you the speed of light, we give you the mass of everything, we give you, okay, it's not about memorizing numbers. It's about knowing the fundamentals. Okay, well, there seems to be some confusion, but most people said 2, which was the kinetic energy of the neutron and the rest energy of the neutron. And that's correct, but how did you know that? How did you decide that? If you said it was the kinetic energy of the neutron and the rest energy of the neutron, yeah, we just look at the system in the initial state and see what's there, right? That's what you're saying. So initially, this is the initial state. It's a neutron. None of that other stuff is there yet. So all we've got is the neutron, and the only thing it can have is kinetic energy. So we have kinetic energy of the neutron and the rest energy of the neutron. Okay, questions about that? All right. So what goes on the other side of the equation? The final state. Okay, well, people seem more sure. And there's a lot of terms, aren't there? It looks like the kinetic energy of the proton and the kinetic energy of the electron and the kinetic energy of the antineutrino and then all their rest energies too. And that's right. We just look and see what's there and then see what kind of energy they can have. They're all particles, so they all have this particle energy. So we've got the kinetic energy of the proton plus the kinetic energy of the electron plus the kinetic energy of the antineutrino plus the mass of the rest energy of the proton, the rest energy of the electron, and the rest energy of the antineutrino. So that's correct. And now, so this is the equation we've got. Where's the unknown? We want to know the kinetic energy of all the products. So what's that? What are we solving for? We just got symbols here. So. Yeah, it's this stuff, isn't it? So we don't necessarily, from this energy principle, we can't necessarily say from the energy principle alone, well, the proton will have this much kinetic energy and the electron will have that much kinetic energy. But we can say altogether, that's what they're going to have because that's... Okay, so now the next thing we do when we're doing a problem is we look to see if anything is zero in our equation so we can... And since we said the neutron was going to start at rest, then its initial kinetic energy is equal to 0. And so now we can actually just put in numbers. Now we're ready to go, right? So we have all this kinetic energy of the proton plus kinetic energy of the electron plus kinetic energy of the antineutrino plus the rest energy of the proton, which is 938.3 MeV, and the electron, which is 0.511 MeV, and the antineutrino, which is approximately 0. And that's going to be equal to the rest energy of the neutron, which turned out to be 939.6 MeV. Now, could this be a negative number? No, it's kinetic energy. It can't be a negative number, right? It can be 0 or it can be positive. So therefore, these numbers better add up to less than that. Okay? Which says that we started out with a neutron with a certain amount of rest energy. The rest energy of the products is less. Some of that rest energy, some of the mass, got converted into kinetic energy. And that, in fact, works out to be correct. And if we solve this, we get all these kinetic energies is equal to 0.8 million electron volts. It's this. So if you multiply out, the way you get this number is you take the mass of a neutron to many significant figures, and you multiply by c squared, and you get some number of joules, which is really fairly small. So you say, okay, I'm going to divide by that and express it in million electron volts. Okay. So yeah, rest energy has that c squared in it. So really, there's not much to it, unless you fail to notice that there's a change of identity. Do you have questions about this? You'll probably get to practice this at some lab. Okay. In order to make sure that we really do a serious job on introducing potential energy and get through gravitational potential energy, which you will need for lab at the beginning of next week, I'm going to ask you to read a section of the chapter. So there's a proof. There's section 6.6 is just a demonstration that the energy principle is consistent with the momentum principle. That's okay. Section 6.7 is work done by a force that's changing, like the force due to a spring or force due to a gravitational force that varies with separation. We're not going to, so you need to read that. We're not going to go over it in detail. We'll end up using it a little bit at the end, but we really want to get to potential energy because this is such an important topic. So potential energy, notice that there isn't anything called potential energy here when we're talking about a system that's one object. Okay, it's going to have kinetic energy, it's got rest energy, and that's it. So potential energy is the energy associated with interactions of more than one object within a system. So in order to establish the need for potential energy, let's consider a really simple situation and just work through it and see where we get to. So we're going to consider a situation where we have a ball near the Earth and we drop it. Okay, it's pretty elemental. We saw when we were working with the momentum principle that we got to choose what we'd consider to be our system. Often we'd pick one object to be the system, but sometimes it was useful to pick two objects if they were interacting or colliding or something. Well, that's true with the energy principle too. We get to choose a system, and it better work no matter what we choose as the system.